Okay, I finally got my act together here. One issue was that I didn't take good data, and I was puzzled by the results. I was trying to do it very quickly. So, oops, I'm trying to use my yeah, there it goes. Trying to use my tablet. Okay, so it took a bunch of data here, and I got numbers, and now we need to crunch it through. One thing we have to do is we have to measure the impedance of the device under test, heavy duty, right? So I'll remind you that we have some VN, VN, and that was from the function generator. And it was a sine wave. And we set it up to be 12.7 volts peak to peak. Excuse me. And then we did a variety of frequencies. Not everybody did, but at least somebody from each group had a look. And so the circuit was some R standard, and then we had something like this. We call it there's some box we have here. We call it the device under test, and then it goes to ground. And then what we did is we connected a voltmeter here, the digital voltmeter, because voltage across. And then we connected the oscilloscope, and I can see where I can make myself a little bit easier here. I'll keep that smaller. And then we connected the oscilloscope here to here. And this is because the oscilloscope, the black wire, or the return, is earth grounded. So normally we wouldn't, strictly speaking, this is the return to the function generator. And in fact, the function generator is also earth grounded. So this is the only possible way to do this if we want to use the oscilloscope. The DVM, the digital voltmeter, floated. And it just means that with the red and the black, we could switch them around, but the black is not connected to the earth ground. So that means that the black wire can float to whatever voltage is here, and it truly tells us the delta V here. And that's what we want. We just have to remember that it measures RMS, and the oscilloscope measures peak to peak. So, and this diagram should be in your books, in your log books, which is you handed in already. And there is a table of numbers that maybe some of you have, not sure, don't remember anymore. So now here's our equation up here to use the numbers we measured to produce a measured Z. And remember, Z is called impedance. impedance, and it's just the generalized resistance, and it equals the real resistance plus the imaginary number I times so-called reactance. And so then the reactance for an inductor equals to 2 pi f times the inductance, and the reactance for a capacitor equals negative, which is something we have to deal with a little bit, 2 pi f. And that has to do with the way these things are defined. Originally, it's so-called circular frequency, radians per second. And you may have dealt with that in, in Physics 1100. But we are just going to use frequency. And the thing to notice here is that the reactance gets smaller with frequency for a capacitor, and it gets larger with frequency for the inductor. Okay, now this algebra here has to do with using the total current through each one of these two things. And so it turns out that the current through our standard, if we measure the voltage across our standard, we get the current through there, and that would tell us the I total. And then so the voltage across the device under test would be I total. So V across this is going to be equal to I total times the Z of the device under test. And without getting into it, you can see that, well, no, it's not so hard to see. So if we have, let's see here. Right, I total times our standard equals to voltage across our standard. And remember, it's a series circuit, and we know about series circuits already. And so we can simply substitute in for I total up here. We can rearrange this to be I total equals VR standard STD divided by R standard. And so V DUT equals VR standard divided by R standard times Z of the DUT. And it's somehow I'm getting some strange stuff. My cursor is moving around. And then you can see that I can rearrange that by bringing this over to that side, and then it flips. So it becomes V, again, V DUT divided by VR standard times R standard. And equals Z DUT. So that's where it comes from. We may have gone over this. Okay, so let's go back up here. Now the thing we have to be careful of, though, is that they both have to either be RMS or they both have to be peak to peak. So the first thing we have to do is they have to convert one of these two. And remember that VRMS equals square root of 2 over 2 times V amplitude, which is equal to the square root of 2 over 2 times V peak to peak divided by 2. Okay, whole pause here. All right, now all of a sudden you notice I have a gray sweatshirt on, huh? Oh, excuse me. I was just out having lunch with Jenny on our patio outside. Okay, so what I was saying is that we have two voltages to divide, but one is in peak to peak and one is in RMS, so we'd be trying to add apples and oranges, as it were. So we have to take care of that. And so we have to convert one of them to the other's form, if you will. So why don't we just take, since it'd be right next to each other, we can then just go like this, and then we're going to say P to P. And oh yeah, and by the way, I've published this on Canvas, so you can have what the raw data. Excuse me. I typed in all the values for you here. Okay. So let's see. We need to so V. We have to invert that. So it's let's get the pen here. And so V peak to peak is just take this square root of 2 over 2 and this 1 over 2 and put it on the other side. So they flip over. So that's 4 over the square root of 2 times VRMS. Okay, let's get to it. So, oops. All right. Equals the VRMS times 4 and divided by SQRT of 2. There we go. And let's see. Now, this seems to be violating the rule of the total. Can't the two of them together, the voltage across the R standard, then the voltage across the device under test has to add up to the voltage across the input is 12.7, and that's not right. Let me hold on a minute. Let me check something. Well, anyways, pause finished. You didn't know the difference. There's something not right here, because if I add this and this together, it ends up being more than the peak-to-peak total, which is troubling to me. I think I know. Wait, one more try. Oh well, I just can't figure it out. Part of it is that I generated some of this data artificially, and that's all there is to it. So let's just get through it. So I converted the voltage across our standard to equal to peak to peak, And I think what's could be what happens here is there's something about, see, we're not keeping track of the V total going in, and that's wrong. See, this is not the standard way of doing these things. That's what's wrong. But anyways, that's neither here nor there, because you guys are, it's just not what you're here for. We just want to see a little manifestation of the fact that these are a capacitor and an inductor are frequency dependent resistors. Okay, so we can then get the Z of the L here, and oops, I must have cap locks on. Yep, Z of the inductor, and this is measured, and then we use this equation here, which is equal to the R standard, and we need the dollar signs, times the voltage across the device under test, which is this, divided by the voltage across the R standard, which is that. And so we get a certain Z here. Nice. And I see another issue going on here. So hold on. I've been staring at this for too long. All right, equals R standard F4 times the V across the DUT in peak to peak divided by the V across the R standard peak to peak. And there she is. Okay. There we go. And of course, let's see what the predicted is. And that would be 2 pi times the frequency times the known inductance. Okay. Equals 2 times pi times the frequency times, the known inductance with the F4. And it doesn't match, but lo and behold, it begins to match, so that's interesting, and I'll explain that to you. And let's add a decimal place just to see. Nice, and now they come closer and closer. Okay, so we can copy this. In fact, I think, yep, should be able to just say copy and paste. Yep, because now it does, yep, it converts what we want. And that's one of the reasons we picked to convert this, because now we don't have to change it to voltage inductance or whatever. It's always across our standard. And lo and behold, no surprise there. Nice. Okay. Now, let's see. This one should be the same, right? Yep. In fact, let's copy and paste. Now, let's be a little careful. This is Z of the capacitor now. And predicted is much different. It's 1 divided by, and let's just get the parentheses going on there. And we have to change the E4 to the capacitance. And we can just do that up here. And now, let's see. What did I do wrong? 1 over 2 pi. Frequency is, oops. Where did that come from? Oh, right, that's fine. And let me pick the frequency. There it is, nice. So they look pretty much the same. And let's see, oh, okay. So this one here, copy, paste, and something isn't right there, but we'll get to it in a minute. And that, see, well, I know that's okay. Let's do RLC. And so this is VR experimental divided by B peak to peak. And what I think is that this, right, is it's actually in millivolts. Okay. And let's hit that there. So then that means that I have to divide by 1, 1, 2, 3. There we go. Nice, huh? Okay. Yeah, we goofed somehow. These are in volts or so. I don't remember exactly what happened. Okay, now, ZLC predicted. Now, the Z of an LC circuit is we have to take, we have to add these two together. So it's 2 pi FL minus 1 over 2 pi FC. And what we do is we take absolute value. What you're supposed to do is square the two of them. Square it. They add directly. Well, subtract. You square it, take the square root, but that's the same thing as taking the absolute value. Okay. And so Z, something happened. Z L, oops, LC predicted. And, well, we can just take the ZL and the ZC. Can they be? Yeah. You take the absolute value of the two and subtract one from the other. Oops, something's not right here. This is, oh yeah, because this is not the C, this is the R, EXP. Okay. ZL, oh, we'll make that ZSC. Okay, so now we have the ZL predicted, the ZC. So we can take the ABS of, oops, I forgot to put equal sign, equals the absolute value of the predicted impedance of the inductor and the predicted impedance of the capacitor. And look at that. Looks pretty good, huh? Although you notice that is 0. And there's a reason for that. And what happens is this is the resonance. Did I talk about the resonance yet? No. No, I'm going to do that when I plot something. Okay. So, that's right. You can't see that. So we need to clear some room to make a graph. Hold on. Okay, back again. Wow. This has really been some job work, huh? Okay, so let's see what we can see here. We want to do a graph of several things. So I hold down the control key. And let's see if this thing can do this for me. I don't know. And it looks that way. Nice. All right, so we have all kinds of stuff going on, and I picked, unusually you might notice, I picked the scatter plot with lines, and that was intentional. It's about the only time we do this. And I shouldn't even bother with that just yet, because what we need to do is we want, now this is a little bit difficult to read, and so what we're going to do is we're going to change them. Oh, you can't see that. Hold on. So I double clicked on that, and then I want to I double click on the, or I click now on the axis number is there, and I want to axis options, change it to logarithm, which is also a standard thing to do. And now I change this one to logarithm. Nice, huh? And let's see, we want to make the minimum 100. Yep. And let's make the maximum 50,000. Nice, huh? Look at that. And what else can we do? We have to format series now. So this is the ZC predicted. And Mac users, you come up here, format, and you get the drop-down box here. And now we want to get rid of the markers for the predicted. So the trick here is pick the predicted ones first. And ZL predicted here. And that way these choices will stay right here for you. And what else do we have? Yep, predicted, none. And let's see, I think there's 3 predicted. ZL predicted, ZLC, and ZC, right? Now, for the other ones, actually, I was going to remove the lines, but I think we should keep the lines and the data points. And isn't that interesting? Now, one thing we can do, I learned a new trick today. So I want to fit this guy. I want to make it 2 columns and 3 rows or 4 rows like this. But I want to put measured on the left and predicted on the right. And watch, I figured out how to do it. Select data. And I have ZL measured, ZL, so actually they are just the way I want them. So what is it that went wrong? That's right. this broke the pattern, so I'm going to move that one down. There we go, the Z, our experimental measured, and there it is. Isn't that pretty? And this can be jazzed up, increase the font. Probably want to add a background. There we go. And oh, I guess I picked no fill, didn't I? Pick white, then the grid lines disappear. Oh, another thing that looks nice when you do this, I noticed, was the grid lines. And I want the minor verticals. Yeah, that helps a lot. So, isn't that interesting? Now, one thing is that I mentioned something about a resonance frequency, and when it comes to an RLC circuit, which is what we have here, well, we measured the Z of the LC. And so, without going too much into it, there is a resonance frequency, which is 1 over 2 pi square root of LC. And I predicted that for this circuit, and it's 6, let's see, let's change that to a number. And notice it's 6202.55, very precise, right? You'll also notice it looks like 0 here, but it turns out it's not exactly 0. And I did that on purpose because if I were to copy that and paste the number in right here, it's, well, I thought it would start complaining because it would say that it can't do such a 0. I thought this, because it's logarithmic, I thought it was going to tell me that I can't do a 0 on a logarithmic plot. So it's outrageously tiny. Okay, so that's something to do with computers, and if you know anything about computers, double precision. It's a rounding error that computers do. That's good enough. So let's see, 6202, quite small. And I could just go back to 6200. And it just makes it look more pleasant. What happens is that it bends this sideways because it doesn't have enough data points and this is just I'm not fitting a formula to this. This is just Excel connecting the dots together with smooth lines. So it's not a fit. If it was a fit, then it would be more symmetric about the resonance right there, but it's not possible. Now, also notice that the measured inductance is different than the predicted, whereas the other guys pretty much do what they're predicted to do. And the reason is that that you can't make a perfect inductor. A perfect inductor would have an R equals to 0, but they're made of a length of wire wound around some magnetic core, and so you can't make that. This is impossible. Capacitor, an ideal capacitor, is realizable. It has an infinite resistance, and that's something we would have learned in the capacitor lab. Okay, oh yeah, and then the resonance. What's weird about the resonance is that it's not so much you get some sort of minimum. You would have predicted that the resonance circuit would be right here where they cross, and in fact that is the point. It's the same exact frequency where they cross at 6202. But what happens is, because of the way we calculate the impedance of an LC circuit here, the two of them are exactly equal, and then this number becomes 0. And all the voltage drop would be across the R standard. And this is the basis for a tuner, radio tuner, although it would be wired up a little differently. but it just shows you this notch here. And so we would know that we could, in this case, we would be killing that frequency. Oh no, wait a minute. This is the resistance. So that frequency would actually be not killed because the resistance across those two would be very low. And so we could measure the voltage across the RLC and notice that the voltage across our standard is very high. So that would be what would be our radio signal. It's pretty interesting. And yeah, it's odd because this you would expect it to again to be some minimum because two resistances in series. It's one of those quirks of complex algebra using imaginary numbers. Okay, so anyways, wow, it's gone on to 35 minutes. I've worked really hard on this because I needed to create some more data points, and I had to do that by creating them. I couldn't find data. It's weird. I don't know what happened to it over the years. Oh, and one nice thing here, you see we chose the minimum 0.01, so we could cross it at 0.01. Now we get a more usual kind of graph where this is all the way at the bottom. And then notice that now you could add things like axis titles and that sort of thing. So I'll leave that for you guys, the chart title. And so, yeah, make sure, well, your notebook's already handed in, and I will just say, you know, you might want to take some notes. I don't think that this is super important for your professional careers in the health field or the bio field. It could have something to do with blood flow and things like that, and I'll have to, hopefully in the future, I can try to work that into the curriculum. But I'm just going to ask you to hand in your spreadsheet. Oh yeah, when you download it, notice up here I saved it with my name on it. I'll post the original, the blank one for you. Wow, long one. Good luck.